Good day, I'm Dr. T and welcome to my office. So in this video, I want to talk about work, energy, and I'm going to wrap things up with simple machines. Now, if we want to define work, we got a couple of different ways of doing this, but they all wrap into basically the same concept. We are going to be exerting a force over a distance, or we could say that we are adding energy in a unified way, so that we are moving our atoms all nice and together. In a few videos, I'm going to talk about heat, and that's going to be adding energy where we make things all chaotic. But of course, when I'm talking about energy, I'm going to probably need to define that at some point, and that's going to be this video. But let's start with work. So when we exert a force, obviously we can do mass times acceleration, but the thing might not actually accelerate. It depends if we're able to give enough force to actually get the thing moving. But if we're able to exert a force and it's able to actually move the thing, either by accelerating it or by crumpling it. So in this case, we can do work in the form of accelerating an object, but we can also do work in the form of deformation or squishing an object. So think squishing a spring. It's a little bit more than what we usually kind of narrowly think about this. But the idea is, hey, I can do work on an object. That's great, I can accelerate it. And in many respects, what I'm doing, especially if I'm accelerating an object, what I'm doing is I'm imparting energy from myself and I am putting it onto the object. Energy gets the wonderfully somewhat circular definition of the ability to do work. And energy comes in a whole multitude of types and flavors. I am going to focus on those of the mechanical nature, where I am physically moving a thing or squishing a thing. Whereas in later videos, I am going to focus on other approaches, such as energy from light or electricity or gas pressure, which is kind of moving a thing, to be honest. So I could kind of loop that back into this video. I might. We'll see. Okay, so if we're thinking about accelerating things and we're thinking about forces, let's look at kind of the forces we talked about previously. We talked about exerting a force by pushing or pulling something, and I guess maybe just calling it the thing is maybe not the best way to do this. Let's actually use some technical terminology. The thing, what we're talking about, we call that the system. And so if I'm doing work on the system, that means I'm probably imparting energy into the system. The system, however, could do work on me, and in this case, I'm going to call it me and everything else. We're going to call that the surroundings. So if it's doing work on the surroundings, so if the system is doing work on the surroundings, then we would say, it's giving energy off. It's giving energy to the surroundings. Fun fact, energy is conserved. So whatever I give off, somebody else must take in. Now, right now I'm focusing on work, the nice orderly motion. Later on, we'll deal with heat. Energy is conserved, work is not conserved. I can convert work into heat, the good old rub your hands together, get them nice and toasty. So that is definitely a thing, and we'll get there. But for right now, we want to keep in mind that whatever energy we're putting in, we're going to get out in one form or another. So I've got the option to push something and to accelerate it, and this leads us into kinetic energy. So if something is moving, then it could sacrifice some of its velocity to then do work on something else and, say, accelerate that something else. Two things bumping into each other. I think in the last video I had this GIF of boxes bouncing back and forth. So something like that. So kinetic energy, we look at that one and we do an equation that is along the lines of kinetic energy equals 1/2 the mass of the object times the velocity squared. And this is actually going to become really important here when I look at one of our case studies here. So how fast you're going, the faster you're going, the more energy you're going to have. Or the bigger you are, the more energy you're going to have. Now, the other area that we talked about was gravity pulling things down and gravity accelerating things down in, say, free fall. And so gravitational potential energy, that is going to be described by the acceleration of gravity times the mass of the object that's accelerating. So on Earth, gravity accelerates at 9.8 meters per second, and we're going to times that by this mass, which, if you think about it, that's the force. So gravity times mass is force. Okay, and then we're going to multiply that by the height. Basically, how far does it have to drop? This is one area where we want to kind of think about, again, that everything is relative. How high something is Well, it depends. If I'm on a skyscraper with a table and a book on the table, well, how high is the book up? Is it from the height from the table to the floor or from the table to the ground? So that h is how far it's going to fall. But that is relative. There's no real absolutes in everything. Everything has got some relativity going on here. From kind of what's your point of view? Where's the floor? And that's going to become very important in a few modules over. So I've got two forms of energy. I could switch between the two. I want to introduce a couple of extra ones. So if I have a spring, I can squish the spring and I can store energy in the squished spring. And so that one is going to be potential energy equals 1/2 the spring constant, basically how squishy is the spring, times the displacement, which is usually given in x squared. So basically, how much did I squish the spring? I'm going to square that. The harder you squish on the spring and the further you squish it, the harder it squishes back. Okay, I mentioned gases. This I'll probably stick in the gas content, but I don't cover that in all of my classes. So I will point out that when it comes to gases, the energy or the work being done from a gas is going to be the volume changing of the container. So think like a piston, and so as the piston expands, that's the volume change multiplied by the pressure. And this is assuming a constant pressure. If you have, not constants, that does make things just a smidge more complicated. Okay, so we've got a few different equations for energy. Let's start using some of these by switching them back and forth, because remember, energy is conserved. And one of the classic examples is what I've got over here, a nice pendulum. Now, this is one of those pendulums that swings back and forth and the Earth rotates under it, but you don't have to be nearly that fancy. A pendulum is what we call a harmonic oscillator. It's one that takes energy in one form, converts it to another, and then back and forth over and over again. Conveniently, very consistent in terms of time. The pendulum swing is actually very nice and consistent. We use that for timekeeping for some older style clocks. Okay, so here's what we're going to do. When the pendulum is high up, it's got a lot of gravitational potential energy. Basically, I'm holding the pendulum up, it's got gravitational potential energy, and I let go. Gravity is going to be pulling down on it. It's going to be accelerated towards the ground, and so it's going to start exchanging that gravitational potential energy for kinetic energy. And as it does so, it's going to go faster and faster. Eventually, it hits the bottom of its swing, and it's going to have no more gravitational potential energy. It can't fall any farther. The cable is holding it up. And now it's going to start swinging out, and the cable is going to pull it up in the process. So it's going to start exchanging kinetic energy for gravitational potential energy. Now, it's going to be shoving the air out of the way. It's going to be warming up due to friction and air resistance. So the amount of energy is going to go down slowly, hopefully slowly. It depends on how well lubricated your pendulum is, I guess. But now it's going to slowly slow down. So it's not going to quite reach as high as it did to start with. It'll get close, but not quite. And it's going to swing back. And it's going to go from 100% gravitational potential energy, which is a slightly bit less than what it started out with. And then it'll go more and more kinetic potential energy, less and less gravitational, until it's back at the bottom, where it's going almost as fast as the last time it was there, and it swings back up and it goes back and forth. But here's an interesting feature. Because energy conserved, it's not created or destroyed. You can switch energy out for matter. We're not going to do any E equals mc squared nuclear physics stuff, as mentioned previously when we talked about chemistry. But because energy is conserved, as long as nothing else does work on that pendulum, you don't give it a shove, well, the interesting feature is that it will never go beyond the height that it started out as. There's an interesting physics demo. I haven't done this in years, but there's a really cool one where you get a nice strong cable and a bowling ball and a wall. You put your head against the wall, you bring the bowling ball up. Now the cable needs to be tied off to the ceiling, and you let go. You take it right to your face and you let go. So it's going to swing out, it's going to swing. And this bowling ball is coming straight at your face. But it will never hit you. As long as you didn't push and as long as you don't lean your head forward. That's actually what the wall is there for. You do not want to lean forward, whatever you do. The bowling ball can't go higher than it started. So as long as you didn't push it, you didn't do any work on it, you just let it go, then it's going to alternate back and forth, never actually hitting you in the face, which it makes a cool demo. A little creepy, a little spooky, but really a cool demo. Now, the interesting feature on pendulums, of course, is that the higher up they've got, the more energy they've got, the faster they're going at the bottom, but the further they have to go. So as they slow down, they don't go up as high, so they have a slightly lesser arc, and that ends up canceling out so that the swing of the pendulum is nice and consistent, which is why they are useful for clocks. Of course, we don't have to use an alternation between gravity and kinetic energy. We could do spring potential energy and kinetic energy. And that's actually how some older watches work. They have a device that wiggles back and forth with springs. So a harmonic oscillator does not have to be a pendulum. It could be a ball on a spring, a good old pogo stick. Actually, when we run, our tendons act springy to be a little bit of a harmonic oscillator, so we don't have to put all that energy in. We're not wasting some of the energy as we go thud on the ground with every step. It's an interesting feature. Now, we looked at the equation for kinetic energy, and that's got a really interesting feature. Remember, force is mass times acceleration, and kinetic energy is going to be mass times velocity squared. So if I want to accelerate something, I'm going to need a force. But also, that means it's going to push back against me. For every action, there's an opposite equal reaction. So if I take some energy, maybe some chemical potential energy, I'm going to burn some fuel. I'm going to get some energy out, and I'm going to heat up some gas, and I'm going to shove it out the back end. So I'm going to accelerate some gas out the back end. I'm going to be pushed forward. And this is how a jet and a rocket work. Jets suck air in from the front and shove it out the back with a little bit of fuel to make it hot. Rockets carry everything with them and just shove it out the back. We'll do more on rockets later. Once again, I like to put all the space stuff in the space stuff, although rockets don't have to be in space. But let's talk jets here real quick. If you look at an old jet, they usually have these like long, narrow jet engines, and these are turbojets. Turbo basically means turbine, the spinning fan blades in the jet. And so anytime you got this, spinning fan style, we like to put turbo. A turbocharger is basically an air pump that spins fans to push air into your car and make it run faster. In this case, we got a turbojet. And so you get some fans, you spin them, they suck air in from the front, you ignite some fuel there. That's going to give you some chemical energy. They'll turn into heat that you can then turn into work. And then that's going to shove out the back end, and in the process you turn some more fans to power the whole system. So you spin it up to start with, and then the back end fans take over. And those work really well, very, very efficient, but the more force you want forward, you either need to move more gas out the back end or you need to move it out faster. But the faster I shove it out the back end, that's going to take lots and lots of energy, but I want force. I don't need energy per se. I want energy, but I want force. So if I wanted to be really efficient, what I would want to do is suck more air through. So nowadays, quite often, we try and suck more air through the jet engine to be more fuel efficient. The fuel is one of the major expenses of flying an airplane. And so now we use turbofans. So in this case, we're going to modify the jet engine so that instead of just sucking all the air, throwing it through the combustion chamber and out the back end, because frankly, the combustion chamber is only so big, you only need so much air. You can put a lot through there, but you want more air. And so we're going to extract more of that energy by making that air flying back, turn the fan, and we're going to suck more in there. And so we're going to use a turbofan. And so some of the air goes around the combustion chamber, around the jet engine, so we can shove even more air out the back. Because remember, kinetic energy is mass times velocity squared. It's going to be more efficient to shove more air than to shove the smaller amount of air faster. Now we can go even more extreme. We can do a turboprop. So instead of having a big fan, we can use a giant fan. We can use a propeller, and we'll probably put that on like a gear shaft so it's not spinning at some stupidly, ridiculously fast speed because jets spin fast. And now all of a sudden we can use the efficiency of the jet engine to power a giant propeller, and that gives us great efficiency. It doesn't work great at high speeds. It's a nice slow approach where the jet works better at high speeds. But yeah, we can use this idea of looking at velocity and kinetic energy and mass and thinking about, well, how we want to do some trade-offs. And this is one of the themes of this video is we're going to be looking at the physical world. We are locked in by the laws of physics. We can't control how nature works, but we can decide trade-offs. We can, do a little bit more of this, a little bit less of that, and try and get a system that works better for us. Okay, so By the way, there's more types of jet engines. I only brought up kind of the three big ones, and some of those are jet engines. They're a jet. They just got other things hooked on them. But let's move on. Okay, so I've got energy. If I want to store energy, well, I've got a couple of options. I could have a big heavy thing and put it up high, and that's going to store some energy for me. That works. By the way, the big heavy thing is usually water. So if you look at a hydroelectric dam, they're a battery because you pump water from the bottom up to the top, as well as, you let the rain fill it up. And now you've got a bunch of water, and you can let it out and extract some of that kinetic energy of the water flowing out the bottom and turn that into electricity, which will be in coming videos here shortly. So if I want to store energy, I can just take big heavy thing and shove it up high. Alternatively, I could take a bunch of gas and shove it in a tube and let the pressure out. Change in volume times pressure gives you the amount of energy given off by a gas expanding. But I can actually store my energy in the form of kinetic energy. Now, having a big thing just zipping by is kind of inconvenient, but remember how I mentioned last time everything we think about in linear terms also exists in angular terms? Well, instead of having a big thing zooming by, I could have a big thing spinning, and the faster I spin that, the more energy I store into it, or the heavier it is, the more energy I store in there. And that is what we call a flywheel. And these things are everywhere, especially when you get energy out that comes in bursts. So quite often, if you've got an engine that's doing chemical energy and it's doing combustion, if you look at an internal combustion engine, they're like almost exploding. They're not exploding. You do not want to detonate. That's called knocking. That's bad. That breaks stuff. But you get this pulse of energy. But as you're driving along, you don't want to do this like pulse, pulse, pulse. You want a nice smooth flow. So as you're pulsing, you want lots of spinning metal to act as a flywheel. You may have a dedicated flywheel, or you may just have big spinning metal to act as a flywheel. Store up some energy and let it out slowly. There's even thoughts of using these for grid power storage. Big flywheels, make them spin, and then you put energy in by spinning the motor, or you turn the motor into a generator and you get some energy out by slowing them down and get some power out of that. In fact, we kind of do that with most of our power plants. Most electrical power plants involve a turbine of some sort. So, that circular fan, that's a big piece of metal and it's spinning, and so it's storing some energy. So when somebody flips on a light switch, the electric load increases just a little bit. You're going to suck out some power from the system. You need a little bit of energy stored to give you just a hint of time to put another coal on the Barbie, or crank up the natural gas, or another fuel rod on the reactor, and well, that's your giant piece of spinning metal. Works quite well. So we can store energy in several different ways. If we think about energy, we can store it. And if we can store energy, hey, we can convert it into another type of energy. And that's one of the major narratives that we're going to be going through in the next several videos with this, is how do we store energy in things, or how do we switch energy back in? Now, when we're talking about energy, I do want to bring up a couple more terms. Generally speaking, I talk about the terms energy, and that's the ability to do work. But there's one more term I need to bring in, and that's called power. Power is energy per unit time. So how much energy can I bring to the party in a given amount of time? A Snickers bar contains more chemical potential energy than a stick of dynamite. But you can get that stick of dynamite's energy out in a fraction of a second. That Snickers bar is going to take you an hour or more. It takes a while to digest that thing. As such, power is the ability to deliver energy quickly. Now, sometimes we get into an interesting problem. We have all the energy we need, but we can't get it to where we need it fast enough, so we lack the power. Or alternatively, we got plenty of power. We can get the energy quick there, we just don't have enough. And so, we need more of that. And so sometimes what we're going to be dealing with is thinking about both the total amount of energy and then the flow rate. How fast can we get that energy to where it needs to go to get what we need done? And so that is the concept of power. And with that, I want to jump into a discussion of simple machines. So simple machines are an idea that dates back to the Renaissance, and so we'll call the 6 classic simple machines, or the 6 Renaissance simple machines. We're going to have those up here. And with these guys, they have a couple of commonalities to them. Okay, so just listing off the 6, we've got the lever. It's going to have 3 classes. I'm not going to go into first, second, third class levers. We've got the wheel and axle, which is really unfortunately named. I'm going to get into that guy. He is incredibly unfortunately named. We've got the pulley, the inclined plane, which I do want to talk a bit about stairs after a while, but I'll get there. The wedge, which is basically like the inclined plane, and the screw, which is basically like the inclined plane meets the wheel and axle. Well, kind of. It's the rotational version. Okay, so with these guys, what they have in common is, one, they're really old. That picture is from 1919. And those were old back then. You know, these deal from the end of the Middle Ages kind of thing, if not well before. Levers have been around for forever. You know, our limbs are levers. There's levers all over the place. But the idea here is that these are going to do 1 or 2 functions. And so those 2 functions are quintessential for a simple machine. One, it needs to be simple. You can't be like a whole bunch of stuff going on. You're doing 1 at a time. This is a simple machine. We're going to build more complicated machines out of these, as well as other affiliated materials. But 1 is a force redirection. So if I look at a lever, if it's the first class, you know, the fulcrum in the middle, then I push down on one end and the other side goes up. Simply redirecting the force can be incredibly valuable. Sometimes it's easier to push than pull, or pull than push. And so this allows me to do what works with my system better. Also, sometimes I can stage things. So I can pick my body up, I can grab the rope for the pulley, and then I can lean back down. That way I'm not fighting gravity and trying to lift the big box or whatever. Although simple machines having a ratcheting function is not really an inherent part of a simple machine. It's a valuable tool, but when we're thinking of simple machines, some kind of ratcheting feature like making something into 2 steps isn't, strictly speaking, part of a simple machine. Although a lot of them will do that. The other kind of quintessential one, and really the more definitive one, is they gain what we call mechanical advantage. This is a case where, if I remember, work is force times distance. I can use this to my advantage. If I lack the ability to have enough power to do work quickly enough, or the ability to exert enough force at a given moment, well, instead of exerting a lot of force or trying to generate a lot of power, what I will do is I will exchange that for distance. So I will either exert my energy over a longer period of time, or I will exert a lower force over a longer distance. So I'm able to do the same amount of work. I never cut back on my work. It is always the exact same amount of work, the exact same amount of total energy involved. But what I can do is I can use a lower force to do what I need to get done, but I'm going to have to sacrifice that for distance. And if I've got a power constraint, this may very well allow me to address my power concerns. I may be able to express the same amount of energy, just with a lesser power. Now, simple machines, if they can't do force redirection, or even if they can, the key part is the mechanical advantage. So I want to talk about these simple machines and discuss how they gain mechanical advantage, as well as the equations used to get that. Okay, let's talk the lever. So if you've got the lever, you've got an effort arm, a load arm, and a fulcrum. And so what you're going to end up doing is you push on the load arm or pull. Once again, this can go in either direction. And then that's going to rotate around the fulcrum. Remember last time how I mentioned like everything is about torque? We're doing torque here. And it's going to move the load arm. So effort arm, around the fulcrum, load arm. Now, if the effort arm is long, that's going to have a long distance, and the load arm is short, it's going to have a short distance, then I'm going to gain a mechanical advantage. If it's reversed, I get a fractional mechanical advantage, which you might off the hand think, wow, that sounds terrible. But imagine I've got plenty of force, I want to move the distance quicker, or I want more dramatic swing for distance. Well, in that case, I would want a mechanical advantage that is less than 1. I would want a fractional mechanical advantage. The equation we do for a lever's mechanical advantage is going to be the length of the effort arm divided by the length of the load arm. Okay, let's look at inclined planes. So an inclined plane, it's a ramp, it's a slope. And with this one, what's actually gaining you your mechanical advantage, or kind of the way this is helping you cut back on the amount of force, isn't torque. So this is one that does not involve torque. Instead, this gets back to the idea of normal force. Remember how normal force is the force resisting clipping through the material? Well, if it's flat, the normal force is pointing up. This guy is perpendicular to the surface. But if it's at an angle, the normal force is pushing off at an angle. Now, we can do a bunch of triangles, but basically what that ends up meaning is that it is supporting part of the weight of your material that you're trying to shove up the inclined plane, meaning you don't have to push the whole weight straight up. Also, once again, you can push at an angle, which may very well be much better for you. Your force isn't going straight up, it's going at an angle. So we are redirecting the force, but at an angle now. And it's taking some of the load, but you're going to have to go a longer distance for this. The mechanical advantage for an inclined plane is simply going to be the length, how long it is, divided by the height. Now, let's talk stairs. This is one where it gets complicated. This is one of those cases where it's an example you do not want to use with your students. Avoid this example. An inclined plane, you've got the nice slope, you got the normal force kind of off at an angle. Now, stairs are definitely an inclined plane if you were to drag them up with, say, a sled. But that's not how you normally use stairs. Let's just be honest. Normally you walk up the stairs. Well, there's a couple things going on. One, the normal force is going straight up on stairs. Remember, they're flat. And second, if you think about how you actually take a step, you go up a stair, and then you go up the next stair, and then you go up the next stair, and you go up the next stair. In this case, you've got this ratcheting action, which is not really a key part of simple machines, where you're taking the big thing and you're breaking it into small parts, but you're still exerting the exact same amount of force, just over a shorter distance multiple times. So you haven't really gotten a mechanical advantage. And then let's also address the elephant in the room. Your legs are levers. This is not a simple machine anymore. Anytime you've got walking going on, we've passed simple, because your legs are intricately involved in going upstairs. So in this case, stairs become kind of a convoluted mess. You can argue back and forth about them being a simple machine, which makes them a terrible example to bring up in your classes. So avoid stairs when it comes to explanations of inclined planes. They're great for getting up from one floor to the next, but they're not great for explaining inclined planes, unless you drag something up the stairs. But like, why are you doing that? Let's move on to the wonderful world of pulleys. In this case, you've got the wheel and you're pulling the rope. Oddly enough, this is not really a torque thing. The wheel, it doesn't actually need to be a wheel. It just needs to be a low friction environment. So you could just have a block there, just something to slide the rope across, or the chain, or whatever long flexible thing you've got. So in this case, this is definitely doing force redirection. So if you go over one wheel, and in this case, we got like fixed wheels and movable wheels. So if you go over a fixed wheel, or really if it's a movable wheel, a single wheel, you're going to change the direction from one way to the other. Now, if I look at my setup, I can figure out mechanical advantage by looking at the number of ropes going up. Basically, how many ropes or how many connections are affixed to the ceiling wherever I'm holding this up, or to whichever point I am pulling from. So I've got the one that I'm holding, and then however many other segments of the rope are connecting to the top bit, or to the stationary part of this pulley. If there's only one, then I'm not going to get a mechanical advantage. But if there's multiples of them, then my mechanical advantage is effectively however many ropes are holding up my weight, not counting the one I am holding. Obviously, it's the same rope. Don't get me wrong. Well, usually. Sometimes it's not, but usually it is. So this way I can count them, and I can get my mechanical advantage quite nicely with pulleys. Okay, let's go to the wonderful world of screws. Now, here's another one with a bit of a semantic going on. But a screw is basically an inclined plane wrapped around a cylinder. So we are going to use a twisting force, and we're going to redirect that to a linear force, which is actually quite helpful. If you think screwing a screw into the wall, that's exactly what you're doing. The screwdriver spins, and the screw goes into the wall. So the mechanical advantage of a screw is going to be given by 2 pi L divided by P. L is going to be the length of the effort arm, basically how you're twisting, when you're doing a torque, how far around are you twisting? And then P is going to be the pitch, the distance between the threads. So if you got a lot of threads packed in tightly, you're going to get a very slow moving screw, but then it's going to have a lot of force. If they're very coarse, you're going to have a very fast moving screw, but you're not going to get a lot of mechanical advantage going on here. Okay, now I mentioned there's a bit of a pneumatic issue, and I kind of use the example. When you're screwing a screw into a wall, that's a simple machine. But while it's in the wall, it's not moving. There's no mechanical advantage because it's not doing anything. It's just sitting there. It's acting as a fastener. So it's quite helpful to think of screws while they're in action as a screw, but while they're just sitting there doing their job of fastening things together, they're a fastener. That's a different narrative. They've got forces exerting on them, but they're not moving. They're not doing the job of a simple machine at that point. They're doing the job of a fastener. Now, let's talk wheel and axle, and then we're going to get into gears, because those are not generally on the list of classical simple machines, but they very much are simple machines. But let's talk wheel and axle, because it's the two are fairly similar. And with them, their equation is going to be very much the same as the lever, because a wheel and axle is kind of like a round lever. And here's where we've got some semantic things to deal with. A wheel and axle is not what's on the bottom of my chair that lets me scooch. Those are wheels, those reduce friction, and they have axles, but a wheel and axle always has 2 parts. It's effectively 2 wheels stuck together, so they rotate together. One wheel, the big wheel, is going to go a longer distance than the little wheel. The big wheel is the wheel, the little wheel is the axle. So the mechanical advantage of these guys is going to be the effort wheel, whichever one you are turning, divided by the one that has got the load on it. So if we think of something like a windlass, where you get a big wheel and then the little wheel, the axle, is hooked to a rope and you wind up the rope by turning the big wheel, think like a well that you're pulling it up, or a ship's anchor is being pulled up by. In that case, if you're turning the big wheel, you're moving at a longer distance, but you're exerting more force on the thing you're trying to coil up into the axle, or the little wheel here. Now, the naming of this thing is definitely unfortunate, because it's very easy to think that the wheels in a car, especially the back wheels, the ones that just roll, those are wheels and axle. They have an axle and they're wheels, but they're not a wheel and axle. I wish this was called something else. I can't change this. This has been this way for a very long time. But the idea, the simple machine, the wheel and axle, is not just a wheel and axle. It's really 2 small wheels. Well, you know what? We've really got 2 small wheels. In a wheel and axle, they're fused together. They rotate together. They rotate at the same angular rate. What if we separated those out, though, and we rotated them by, say, putting teeth on them, so they stuck together and they rotated, instead of at the same number of revolutions, they rotated the same distance. Congratulations, you've got yourself some gears. Okay, mechanical advantage on the gears is going to be the number of teeth. These are one of the easiest ones to do. The number of teeth on the output gear divided by the number of teeth on the input gear. Now, these are quite often left off of lists of simple machines because they're not the 6 classical simple machines. The idea of a simple machine, you can go fairly technical and go like, well, 400 years ago, what were the simple machines? Or you can go for, well, what has a simple machine, or what is doing the job of a simple machine? And so if I'm looking at gears, they're definitely doing simple machines. You've got mechanical advantage, you've got force redirection. Remember, one gear spins one way, the other gear spins the other way. You've just redirected your force. Oh yeah, it's all about torque again. But they're not the classic 6 simple machines. So as such, it depends on how you're teaching. This may or may not want to include the gears, but something where this is an obvious question for a student because they're blindingly obviously a simple machine. So you want to have a narrative when your student goes, hey, what about gears? Or what about belt drives or chain drives, things on the bottom of a bicycle. That's a case where you want to come up with a narrative. Are you going to go, yes, they're simple machines, but they're the new ones? Or do you want to go like, yes, they're basically like a simple machine, but the simple machines were defined long ago. I don't know how you want to address that. It's going to vary depending on context, etc. But you still get this idea of mechanical advantage going on with these guys. They function very much as a simple machine. I would say they are definitely a simple machine. They're just not one of the classic or Renaissance era ones. Okay, so looking at the last of my notes, I think I've hit things, everything on the list to cover, and hopefully not too horridly incoherent, only partially incoherent, I hope. So with that said, I will see you in later videos, and have a wonderful day.